Welcome to Gradient Canvas. Today we're going to learn about tokenization, how a language model actually reads your text, and why the same system that can write an essay can't count the letters in the word strawberry. Here's a question that has embarrassed some of the most powerful AI systems on Earth. How many times does the letter R appear in the word strawberry? Look at it. Strawberry. It's 3. But for years, if you asked a large language model, the confident answer came back: 2. The same system that can write poetry, debug code, and pass the bar exam, tripped up by a question a 6-year-old gets right. The interesting part isn't that it failed, it's why. The answer isn't that the model is dumb, it's that the model never actually saw the word strawberry, not the way you just did. Before a language model reads a single thing, its text is chopped into pieces called tokens, and every piece is swapped for a number. That's all the model ever receives, a stream of numbers. It's reading the world through a translator that speaks only in IDs, and the translator throws the letters away. So how should you chop up text? The obvious first idea: 1 token per letter. Simple, 26 symbols and you're done. But then even a short sentence becomes a huge stream of tokens, and the model wastes most of its effort just gluing spelling back together. So try the opposite: 1 token per word, much shorter. But now your vocabulary has to contain every word that exists, plus every plural, every tense, every name, every typo, every language on Earth. It never ends. And the first time someone types a word you've never seen, you have no token for it at all. Real tokenizers split the difference, and it's a lovely compromise. Words that show up constantly, the cat transformer, each get their own single token. Rare or unusual words get broken into smaller familiar chunks, so strawberry becomes berry, and a monster like anti-disestablishmentarianism shatters into 6 pieces. Now a fixed vocabulary, often around 50 to 100,000 tokens, can spell out literally any text you throw at it, including words it has never seen. Frequent things are efficient, rare things are still expressible, nothing is ever out of reach. Where does that vocabulary come from? Nobody types it out by hand. The tokenizer learns it from a mountain of text with one beautifully simple rule: start with nothing but single characters, then find the pair of neighbors that occurs most often, and glue it into a single new token. Repeat. To next to H becomes the next to E becomes the. A few thousand merges later, the most common patterns in the language have fused into whole tokens, while the rare stuff stays in little pieces. That algorithm has a name, byte pair encoding, and it earns its own video. For now, just hold the picture. Frequent pairs merge, rare pairs don't. Once the vocabulary is frozen, tokenizing is just a lookup. Each token maps to its ID, really just its row number in the vocabulary. That ID is what enters the model, and the very first thing that happens inside is that each ID is turned into a vector, a list of numbers that stands in for the token's meaning. That step is embeddings, its own video. But for today, notice what's already gone. By the time the model starts thinking, strawberry isn't a word, and it isn't letters. It's 3 vectors, one for str, one for aw, one for berry. And now the strawberry mystery solves itself. To count the R's, you need to see the letters, but the model never gets the letters. It gets star, aw, berry. 3 opaque chunks. The 3 R's are trapped inside those chunks, 1 hidden in str, 2 hidden in berry, and nowhere is there a single countable letter R sitting on its own. Asking this model to count the R's in strawberry is like handing you 3 numbers, 496, 675, 15717, and asking how many R's are in them. You simply weren't given the information. It was never a reasoning failure. It's a vision problem. The letters were gone before the thinking ever started. Once you can see tokens, a whole family of odd behaviors clicks into place. Spacing matters. Token at the start of a line and space token with a leading space are 2 different tokens with 2 different IDs. Capitalization matters. The with a capital and the in lowercase are different tokens too. And numbers get carved up in ways that have nothing to do with arithmetic. 1, 2, 3, 4, 5, 6 splits into 123 and 456. That alone is a big reason models fumble long multiplication. The digits aren't even grouped the way we group them. Here's the part that reaches your wallet. Everything about a language model is measured in tokens, not words. The context window, how much it can hold in mind at once, is counted in tokens. And when you pay for an API, you pay per token. A rough rule for English is about 4 characters per token, or 3/4 of a word. But that rule is deeply unfair across languages. Tokenizers are trained mostly on English, so English is cheap, while the very same sentence in Japanese or Hindi can cost several times as many tokens. Same meaning, bigger bill, less room in the window. Even a single emoji can cost 3 tokens. Let's count one for real. Take the sentence. The quick brown fox jumps over the lazy dog. 9 words, but 10 tokens. Why 10? The full stop at the end is its own token, and every word except the first carries its leading space baked in. Look, the capital up front and space, the lowercase later, different tokens, even though to us it's obviously the same word. This little strip of 10 numbers is quite literally everything the model receives. From here on, it is all arithmetic on IDs. So, tokenization in one breath. A model can't read text. The text is split into tokens from a fixed learned vocabulary, and each token becomes a number. Common words are single tokens. Rare words shatter into pieces, and the whole vocabulary is grown by greedily merging the most frequent pairs. That one design choice quietly explains the letter counting failures, the arithmetic slips, the leading space quirks, and your token bill. And it is the very first thing that happens to every prompt, before attention, before prediction, before any of the magic. And it is the very first thing that happens to every prompt. Your text becomes tokens, the tokens become numbers, the numbers become vectors, and only then does the transformer start doing the clever part, mixing those vectors with attention to build meaning. Tokenization is step 0 of every large language model. Those vectors are where we go next. Thanks for watching. This is Gradient Canvas, where we make AI beautiful and understandable. If you enjoyed this and want to understand AI concepts, please like, subscribe, and share it with others. Join us to explore more AI concepts, from neural networks to transformers. See you in the next video.